Tensor coordinate transformation laws. The laws of physics must not depend on the coordinate system arbitrarily chosen by humans. This is the core of the general principle of relativity. However, there is a problem. Whenever we write down an equation, numerical components inevitably appear. And those components change when the coordinate system changes. So what can we do? Einstein's answer was to use tensor equations. Tensor equations have a remarkable property. Once a tensor equation holds in one coordinate system, it is guaranteed to hold in all coordinate systems in the universe. If it holds on Earth, it holds near a black hole, inside an accelerating spacecraft, anywhere. Why is this guaranteed? The answer lies in the coordinate transformation laws. The components of a tensor change numerically when the coordinate system changes. But the way they change follows a strict law. Thanks to this laws, no matter what coordinate transformation is performed, the form of the equation as a whole never breaks down. This property is called general covariance. Now let's look at the coordinate transformation laws for tensors concretely. Using the velocity vector as an example, we will confirm what transformation laws the contravariant components and covariant basis vectors each follow. How these two different types of transformation laws together guarantee the invariance of the physical entity. We represent the same velocity vector in both a Cartesian coordinate system and an oblique coordinate system of our own choosing, as follows. The velocity vector has been shown explicitly in both Cartesian and oblique coordinates, with diagrams and equations. Feel free to pause and verify at your own pace. First, let's find the coordinate transformation functions between the Cartesian and oblique coordinate systems. We define the covariant basis vectors in terms of the Cartesian basis as. From here we use Einstein's summation notation, writing Ex equals E1, Ey equals E2 and the coordinates as x1, x2. We attach a prime to the oblique coordinates to indicate they are the transformed system. From the invariance of the vector. By expanding the right-hand side and comparing coefficients on both sides, we obtain the inverse transformation functions, which express the Cartesian coordinates in terms of the oblique coordinates. Comparing with the left-hand side x1 e1 plus x2 e2. Since e1, e2 are independent basis vectors, the coefficients must be equal. Inverse transformation functions, expressing Cartesian coordinates in terms of oblique coordinates. From 1 and 2, we derive the forward transformation functions. These are the forward transformation functions expressing the oblique coordinates in terms of the Cartesian coordinates. Next, let's find the contravariant components in the oblique coordinate system. From the invariance of the vector, we expand the right-hand side in terms of e1, e2. Comparing coefficients. We have confirmed directly from the invariance condition that v'1, v'2 equals 3, 4. Next, we show that the same result is obtained using the coordinate transformation laws. Contravariant transformation law. From the same vector condition, we obtained v'1, v'2 is equal to 3, 4. However, this method has a problem. We have to solve a system of simultaneous equations every time. In curved spacetime or higher dimensions, this becomes extremely cumbersome. This is where the coordinate transformation law comes in, but why does this transformation law hold? Let's derive it naturally from the structure of the velocity vector. Let's find the transformation law for the velocity vector. The velocity vector has the following structure. dx, dy are coordinate displacements, and dt is a scalar that does not change under coordinate transformations. Let's verify this with a concrete example, expressing the coordinate displacements of Cartesian coordinates, x, y, in polar coordinates, r, theta. The coordinate relations are x equals or cosine theta, y equals or sine theta. This is precisely the total differential. Rewriting in Einstein summation notation, x prime, y prime, x prime 1, x prime 2, r, theta, x1, x2. Combining into a single expression using Einstein summation notation. Substituting into the velocity vector. Any vector that transforms according to this law, the same form as the total differential, is called a contravariant vector. This transformation law holds for any coordinate transformation, not just polar coordinates. Now let's verify with the oblique coordinate example. Since the velocity vector in oblique coordinates also takes the form v mu equals dx mu over dt, a coordinate x mu differentiated by the scalar parameter dt, it follows that it transforms according to the same contravariant transformation law. We will now transform the velocity components from Cartesian coordinates to oblique coordinates. Let's expand the contravariant transformation law. From the forward transformation functions expressing oblique coordinates in terms of Cartesian coordinates, we obtain the partial derivatives. Substituting the Cartesian velocity components, v1, v2, equals 2, 3. We have confirmed that the velocity components are correctly transformed by this transformation law. Summary: transformation law for contravariant vectors. Key features. Contravariant components are denoted with upper indices. Has the same form as the total differential, as shown in the previous slides. Examples of contravariant vectors. Coordinate displacement. Velocity. For velocity. For momentum. Derivatives of x mu with respect to a scalar parameter, e.g., dt, d tau, are always contravariant. This is the prototype of a contravariant vector. Covariant transformation law. Before looking at the transformation law for the covariant basis vectors, let's first look at the transformation law for a scalar function. Consider the gradient of temperature. It describes how much and in which direction the temperature changes. In the original X system. In the transformed X prime system. This follows directly from the chain rule. This transformation law has the same structure as the transformation law for covariant basis vectors. Let's verify this. We will now derive the transformation law for covariant basis vectors using the inverse transformation functions. In a Cartesian coordinate system, the contravariant and covariant basis vectors coincide. We will verify that the covariant basis vectors follow the transformation law, which has the same structure as the gradient of a scalar. Taking the partial derivatives of the inverse transformation. Here we substitute concrete values into the transformation law for covariant basis vectors and verify that it gives the correct results. Feel free to pause and check at your own pace. Let's verify with concrete values that the transformation law for covariant basis vectors has the same structure as the chain rule. When differentiating a scalar function f with respect to the new coordinates x prime mu, we apply the chain rule. The form of this transformation law remains the same regardless of what scalar quantity f represents: temperature, energy, or any other scalar. We will verify that the coefficient has the same structure as the transformation coefficient for covariant basis vectors. Here we substitute concrete values into the coordinate transformation of an arbitrary scalar gradient to show that it has the same structure as the covariant transformation law. Feel free to pause and verify at your own pace. Now look at these coefficients. The coefficients from the chain rule exactly match the components of the covariant basis vectors. In other words, the transformation law for covariant basis vectors emerges naturally from the chain rule. This is precisely what we mean when we say that covariant basis vectors carry the structure of the chain rule. Any quantity that transforms with the factor is called a covariant vector, and is denoted with a lower index. Covariant components and contravariant basis vectors. Transformation law. We saw that a vector in oblique coordinates can be expressed in two ways. Let's find the transformation law for covariant components and contravariant basis vectors. We start by finding the concrete values of each. Here we use the duality condition to calculate the concrete values of the contravariant basis vectors in oblique coordinates, and finally verify that the duality condition is satisfied, confirming that the result equals the Kronecker delta. Feel free to pause and verify at your own pace. Finding the covariant components. The covariant components are obtained by lowering the index of the contravariant components using the metric tensor. In an oblique coordinate system, the covariant metric tensor is given by the inner product of the covariant basis vectors. Let's first compute the concrete values of the metric tensor, then use them to find the covariant components. Here we compute the concrete values of the metric tensor and use them to derive the covariant components. Feel free to pause and verify at your own pace. Transformation law for covariant components. Vectors that transform in the same way as the total differential are called contravariant vectors. Vectors whose transformation law has the structure of the chain rule are called covariant vectors. The covariant basis vectors follow this transformation law as well. The covariant components also follow this transformation law. The proof will be given after we study the transformation law for the metric tensor. Here we verify this through a concrete example. Here we substitute concrete values into the covariant transformation law and verify that the covariant components correctly follow this law. Feel free to pause and verify at your own pace. Transformation law for contravariant basis vectors. The transformation law for contravariant basis vectors is uniquely determined by the duality condition. Let B prime nu equal A nu beta, B beta, where A is an unknown transformation coefficient. We want to determine duality condition. The transformation law for A prime mu is already known. Substituting. Setting this equal to delta mu nu. Multiplying both sides by partial x prime mu over partial x sigma and contracting over mu. Left side. Right side. Therefore. Thus the transformation law for contravariant basis vectors is. This transformation law follows necessarily from the duality condition. Let's verify with a concrete example. Let's verify the transformation law for contravariant basis vectors using the concrete example of oblique coordinates. In a Cartesian coordinate system, the contravariant and covariant basis vectors coincide. Substituting these into the transformation law for contravariant basis vectors. This matches the values obtained earlier from the duality condition. Notice that the transformation coefficients are identical to those of the contravariant components. This is precisely why both the contravariant components and the contravariant basis vectors share the same name, contravariant. Summary of vector transformation laws so far. We now generalize these results, derived through the concrete example of a velocity vector, as the coordinate transformation laws for vectors. Transformation law for contravariant vectors. Transformation law for covariant vectors. Note, it is the transformation law that determines what kind of tensor a quantity is. In the present case, these transformation laws define whether a quantity is a contravariant or covariant vector. In other words, a tensor is defined by how it transforms. In the next video, we will continue with the coordinate transformation laws, covering higher-ranked tensors, the invariance of vectors, and why tensor equations hold in all coordinate systems across the universe.